All right, let's dive in. Today, we're talking about something that's all around us, but totally invisible: gases. And we're going to uncover the rules they play by, using this really powerful idea called the kinetic theory of gases. Think about it for a second. What's actually holding up a massive truck on its tires? Or what's keeping a simple party balloon inflated? It feels like nothing, right? Like some kind of invisible force. But it's not magic. It's pure, awesome physics.
The secret isn't one big push. Nope. It's actually a storm, a relentless, chaotic dance of billions upon billions of tiny particles, all crashing around inside. And that's the whole idea behind kinetic theory. It's about connecting the stuff we can see and feel, like the pressure in a tire, to this hidden world of zooming atoms and molecules.
Okay, so here's the plan. We'll start with this unseen world of gases, then lay out the rules of the game. We'll see how all those little collisions lead to pressure, and then make a really cool connection between temperature and energy. After that, we'll put it all into action and wrap up with a quick knowledge check. Sound good? Let's go! All right, first up, the unseen world of gases. This is all about explaining the big stuff, the macro, by looking at the tiny stuff, the micro. So, what is the kinetic theory of gases? At its core, it's a model. And that's a really important word here. It's a way of simplifying reality so we can understand it. It lets us explain physical things, like pressure and temperature, by thinking about what all the individual atoms and molecules are doing. Okay, so if we're going to make sense of this chaos, we have to set some ground rules. Think of it like a game. We're defining the rules for a perfect or ideal gas to make our model work. And to remember these rules, we've got a great little acronym, RAVED. That's R-A-V-E-D. It stands for random motion, attraction, as in there's none, volume, that's negligible, elastic collisions, and duration, which is super short. Let's break those down. Okay, so let's imagine this ideal gas. You've got a huge number of particles, and they're all just whizzing around randomly. They're so tiny that their own volume doesn't even matter compared to the space they're in. They're also completely aloof. They don't attract or repel each other at all. They just fly right past one another until, bam, they collide. And these collisions are perfect, what we call elastic. It's like perfect little billiard balls bouncing with zero energy loss. Everything just keeps going. These 5 rules, they're the bedrock of the whole theory. All right, with our rules in place, it's time for the main event, building the core equation. To do this, we're going to start small. I mean, really small. Let's just think about one single, lonely particle bouncing around in a box. So, imagine this particle. It has a mass, let's call it m, and it's moving towards a wall with a speed c in the x direction. It hits the wall, and, because the collision is perfectly elastic, it bounces off with the exact same speed, just in the opposite direction, so its new velocity is minus c. What's the change in its momentum? Well, you take the final momentum and subtract the initial, and you get 2 times m times cx. That's the key first step. Okay, so what? Well, here's the link. Force is just how fast momentum changes over time. So the more often that little particle smacks into the wall, the more force it exerts. Now imagine not one particle, but n particles, a whole swarm of them. We can add up all those little forces, and what is force spread over an area? It's pressure. The math works out to this equation right here. You can see that pressure, P, depends on the number of particles n, their mass m, and their average speed squared. But wait a second. Particles don't just live on a one-way street, right? They're buzzing around in 3D space, up, down, left, right, forward, backward. But because their motion is totally random, we can make a pretty safe assumption. On average, the motion is split evenly between all 3 dimensions, x, y, and z. This means that the average speed squared in any one direction is just 1/3 of the total average speed squared. This little 1/3 factor is super important. And now we put it all together. We take our pressure equation from before, and we plug in that 1/3 factor to account for the real 3D world. A little bit of algebra, and voila, we get the kinetic theory equation. PV equals 1/3 nmc squared. This is it. This is the beautiful bridge between the big picture stuff we can measure, like pressure and volume, and the hidden, microscopic world of particle motion. This equation is already really cool. But this next part, this is where it gets really good.
This is the aha moment. We're going to connect our brand new theory to something physicists have known about for a long time from just doing experiments, the ideal gas law.
So check this out. On the one hand, we have our equation, which we built from the ground up just using logic and our assumptions. On the other hand, we have the ideal gas law, which came from people actually measuring gases in a lab. Since they're both equal to PV, we can set them equal to each other. Let's see what shakes out. When you do the math, something absolutely profound drops out. The average kinetic energy of a single gas molecule is just 3/2 kT. Let that sink in. This tells us what temperature is. It's not just a number on a thermometer. Temperature is a direct measurement of the average kinetic energy of the molecules. That's it. Hotter literally means the particles are moving faster, on average. Colder means they're moving slower. It's an incredible direct link. Okay, that's a ton of theory. But does it actually work? Let's get our hands dirty and put it into action with a few worked examples. First up, we need to be really careful about what we mean when we say average speed. It's not as simple as you might think. So imagine we have 7 molecules with these different speeds: 2, 4, 6, 8, 10, 12, and 14. Let's run through a few different ways to find the average and see what we get. Okay, look at these results. The simple average, the mean speed, is 8. Easy enough. But look at the mean square speed. That's where you square all the speeds first, then take the average. That gives you 80. And if you take the square root of that, you get the root mean square, or RMS speed, which is about 8.94. So why do we care about this RMS speed? Because that's the one that's directly tied to the kinetic energy and temperature of the gas. It's the one that matters in our equations. All right, next challenge. Let's go big. Instead of one molecule, what's the total kinetic energy in 1 mole of an ideal gas? That's a mind-bogglingly huge number of molecules, all at standard temperature, 273 Kelvin. The logic here is pretty straightforward. We start with the energy for one molecule, which we know is 3/2 kT. To get the energy for a whole mole, we just multiply that by Avogadro's number, Na. And here's a handy trick. Na times K is the same thing as R, the ideal gas constant. So our formula simplifies to 3/2 RT. We just plug in the numbers for R and T, and boom, we get about 3,400 joules. Okay, for our last example, let's get a real-world number. How fast are these things actually moving? Let's calculate the RMS speed for a nitrogen molecule, the main stuff in the air you're breathing right now, at a nice comfy room temperature of 300 Kelvin. So we just take our energy formula and solve it for the RMS speed. We plug in the constants, the temperature, and the mass of one tiny nitrogen molecule, and the number that comes out is just wild. It's 520 meters per second. That's over 1,100 miles an hour. Just think about that. The air molecules in this room are zipping around faster than a jet plane. All right, time to wrap things up. Let's do a quick knowledge check with a couple of typical exam-style questions. Okay, question 1. State 2 assumptions. Easy. You could say the particles are in constant random motion, or that all collisions are perfectly elastic. Question 2. How does this movement cause pressure? Well, it's all those billions of particles constantly smacking into the walls of the container. Each little collision exerts a tiny force, and all together they add up to the pressure we feel. Okay, one last calculation for you. Let's find the RMS speed for a neon 20 atom at 50 degrees Celsius, which is 323 Kelvin. We use the exact same formula. Plug in the numbers for a neon 20 atom at 323 K, and you get 607 meters per second. And you know what? That makes perfect sense. Neon is a lighter atom than a nitrogen molecule, so at a slightly higher temperature, it ought to be moving even faster. The physics holds up. But that leads to one final, really interesting thought. We've been talking about average speeds this whole time, but in any real gas, there is no average particle. You have a whole range of speeds. Some particles are barely moving, others are rocketing around like crazy, and most are somewhere in the middle. So what does that whole spread, that distribution of speeds, actually look like? Well, that's a fantastic question, and it opens up a whole new level of physics. But that's a story for another explainer. Thanks for joining us.